Okay, well, hi, it's Tim again, and welcome to Lecture 8 of Physics 3113, Thermal Physics and Statistical Mechanics. Now, in Lecture 8, we are going to talk mostly about the ideal Fermi gas, but we're going to start out with a little bit of discussion of degeneracies and more importantly, density of states. And this density of states is something you'll use in almost everything we do for the rest of the course. So we'll spend some time with that and explain how that works. And then we'll use that to basically take the continuum limit, that is the limit when we have a very, very large volume of quantum particles, fermions or bosons. And that will allow us to calculate the partition function and mean occupancy, mean occupation numbers in this so-called continuum limit. Okay, let's get started. So we'll sort of review a bit of what we covered last time. So let's start with just a very simple example. We'll consider just one level that has energy epsilon, and we'll consider the case that this can be occupied by a fermion. So, of course, as we discussed in the last lecture, due to the Pauli exclusion principle, the partition function is really simple for one level. It only has two terms because we can only have 0 or 1 fermion occupying that level. Now, we're going to ignore spin for now. We'll see later in the lecture it's very easy to incorporate the case of spin, in particular spin 1/2, when in principle we can have a spin up and a spin down fermion in this level. But that's very easy to handle. We'll get that very quickly soon here. Anyway, so we have our fermion. We can have a fermion in this one level or not, and that gives us two terms in our grand partition function with these Gibbs factors. The 1 and e to the minus beta epsilon minus mu, where mu is the chemical potential. Oh, this is actually a mistake here. This should, of course, this is n equals 1 term here, so I'll correct that when I upload the notes. Okay, so of course we can find the mean occupancy. We just take the partial derivative as we showed in the last lecture, or the last couple of lectures, partial derivative of the log of the grand sum, multiply that by minus 1 over beta, and if we do that we directly get this term. We multiply the top and the bottom by e to the positive beta epsilon minus mu, and we have this form, which you recognized before is the mean occupation number of this level. N in brackets we write it, here was the case of fermions, of course, with the plus sign. And it's also known as the Fermi-Dirac distribution. Okay, we had that last time. Well, it's quite easy to handle the case of degeneracy. That is, suppose we had two levels of the same energy. Well, we can actually consider the case that we have G levels, some number G levels, all with the same energy epsilon. Then we'd have a product of G terms. So the partition function, the grand partition function for these G levels would be just the partition function for 1 raised to the power G, as we've seen before. And so for our case of the fermion, we would have this here, since we only had one term, and we would just raise that to the factor G. And of course, when we take the logarithm of this, we just bring the G out front. And so if we go and calculate the mean occupation number, we just get this factor of G out front. Well, you can take we can take the partial derivative of this. We use the usual rules, and it's just a little bit of algebra. You'll see this simplifies quite easily to just G times the mean occupation number of if there were no degeneracy. So it's very, very simple, right? So if we were to include spin degeneracy, and here I mean spin 1/2, which is what the usual case we'll consider for electrons when we discuss the Fermi gas and we think about electrons in a solid. And so if there's no magnetic field for spin 1/2, the degeneracy would be just 2. Well, this has nothing to do with being fermions. If we had bosons that had some spin, so if it were spin 1, this G would be 3 and no magnetic field, or if they were degenerate. And so, of course, we would have the same thing. We just multiply by G, basically. Okay, so it's quite simple with degeneracy, and especially spin degeneracy, or any other sort of, let's say, fundamental degeneracy, that when the levels are exactly equal. Well, now we're going to talk about what I like to think of as a kind of effective degeneracy, and that will lead us to the concept of density of states. We'll see when we consider systems in very large systems where you have very many particles, the energy levels become very close together, and when we calculate the partition function, we'll have to have a factor that accounts for this sort of density of states, and it kind of acts like a degeneracy effectively in calculating the partition function. We'll see that. So imagine we have a very large system, and the way to imagine that is we have our particles in a box, and we let the volume of this box get very, very large, and if you look at the quantum energy levels, they'll get very close together. We'll see this explicitly in what follows. And so this sort of continuum limit, we imagine our energy levels form some continuum effectively. We'll want to find the log of the grand partition function, and then so this we'll see that we have to integrate rather than sum over configurations. So to do this, we can use configurations labeled by energy, wave vector, or frequency, and we'll see different examples of that depending on which system we use. But as you know, so we have to figure out a way to enumerate the configurations. But as long as we know how that relates to energy, which appears in these Gibbs or Boltzmann factors, these exponentials, then that should not be a problem. So in order to do this, we'll need to know the relevant density of states. That is, the number of modes per unit energy if we have density of states, and if we use energy for the sum over the configurations. We can have density states in wave vector or frequency. We'll see examples of that later in the course. But for now, we'll want to get to the density of states in terms of energy. That is, the number of modes per unit energy. For example, this will be the number of modes. If we consider an interval that spans epsilon to some epsilon plus d epsilon, then the number of modes will be this density of states that we'll call G, to be sort of analogous to the degeneracy we discussed before. So the number of modes in this interval epsilon to epsilon plus d epsilon will be this density of states G of epsilon times dE. So this is the density of states. We'll call it DOS, sometimes in energy. And like I said, for the purposes of determining the partition function, the grand partition function, we can regard this as kind of an effective degeneracy in this continuum limit. We'll see how that works. So eventually that's what we want. We want the density of states in energy, this G of epsilon. But usually one needs to start with some kind of more fundamental variable, that is something that's more directly related to the quantization of energy levels. And once we do that, we can find the density of states in this sort of more fundamental variable, as we'll see. Then we can transform it to get the density of states in energy, which we'll need when we calculate the partition function. We'll see how that works in particular. So we'll consider the energy levels for, let's say, quantum objects in a box, particles in a box, but I say objects in a box. So these could be particles or photons or phonons or really anything that behaves as a wave. Of course, everything that's quantum behaves as a wave in some aspect. especially when you calculate the so-called wave function and quantize the system. So, but think about particles in a box, and we'll actually in later lectures we'll do this for photons and phonons. Okay, so if we have, we get Schrödinger equation, and at some point when we go find the eigenfunctions of the Hamiltonian, then we'll get in the particle in the box, we'll get a sort of three-dimensional wave equation for the time-independent solution, the eigenfunctions, and it'll look something like this. We have this del squared of, let's call the wave function that we're interested in, phi of r. R is 3D boxes x, y, z coordinates. So we have that del squared phi of r plus k squared phi of r equals 0. That's the wave equation. And that describes standing waves. Well, it could describe traveling waves depending on the boundary conditions, but we're going to be interested in particles in a box with infinite barriers, and so this will describe standing waves, more or less. Of course, you probably know the superposition of two traveling waves becomes a standing wave. But anyway, so k here is the magnitude of this 3D wave vector k, and it's related to the wavelength by this relation, of course. K is 2 pi over lambda, and of course we can also have the phase velocity v, which is lambda times the frequency nu, or if we wanted, we could use angular frequency, 2 pi nu, v equals omega over k. We'll use this more when we talk about phonons and photons. Right now we'll just work in terms of this wave vector k for this discussion of particles in a box. So let's consider the wave equation in an enclosure, and just to make life simple, we'll choose a cube that has side lengths L. So each side is a cube, each side is capital L, and we'll have these, of course, boundary conditions where the wave function is 0 in all faces of the cube. So it's kind of like a 3D version of waves on a string. So it's a 3D box. This calculation can be repeated for 2D and 1D. We'll do the 3D version. We might have the 2D version later, or in tutorial or assignment, or so forth. But in 3D, and so the solutions of this equation, we'll need solutions of this equation, and I'll just give them to you. These are the solutions that satisfy the boundary conditions here, and they have this form. It's a constant times these product of sine functions with these variables in x, y, and z. So we have a number of solutions corresponding to different values of this variable n sub x, n sub y, and m sub z. These are all integers starting with 1, 2, and all the way up to infinity, because we need these to satisfy this boundary condition. And we find that in this wave equation, then this k, or k squared here, is pi squared over L squared times these quantum numbers squared, the sum of these quantum number squares here. And so the magnitude of k then corresponds to, we would say that this corresponds to a wave vector. Once we specify these numbers, then we can think of this wave vector k that has 3 components in 3D, which is pi over L times these integer numbers, which specify the levels in this for a particle in a box. And since k only takes on discrete values, we can think of the allowed values of this wave vector as forming a lattice in what is called reciprocal space, or k space as it's called sometimes. You'll see this. So allowed values of this wave vector form a reciprocal lattice. And you will, if you take solid state physics next term or next year, then you'll work a lot in k space and the reciprocal lattice. So anyway, so we have this lattice of allowed values in k space, which represent the solutions to this particle in the box. And so now we need to think about we're going to find the density of states of these k values or these wave vectors, because that's how we started, how we get we enumerate the configurations of our particle in a box, and we'll have to transform that to energy, to density of states and energy, to use that in the partition function. So that's where we're going with this. Okay, and so you'll see, we'll see that so these quantum numbers are positive, and if we look at this quantity, this object here in the parentheses here, basically when we get to very, very large numbers, this forms a sort of spherical surface in the positive quadrant. So you can think of it as like this. So we can think of this in terms of these quantum numbers, n sub x, n sub y, and z, or the k vectors, which are just proportional to that, of course. K vectors are just pi squared over L squared times that. Right, okay. So now, if you think about this, the spacing between points in this reciprocal lattice, this is like my three coordinates on my reciprocal lattice. We see the spacing is basically pi over L between nearest points on the given axis, right? So the closest points are separated by a distance in reciprocal space, which is pi over L. Of course, in reciprocal space, this so-called distance in this lattice has units, 1 over distance. It's a reciprocal lattice. So we can think of basically this quantity pi cubed divided by L cubed as the k-space volume, let's call it, although it has units of inverse volume because we're in reciprocal space. So this is the k-space volume occupied by 1 point, right? We can think as my 1 point in k-space has this little cubic volume. In other words, the density of the points in k-space is 1 over that, so it's L cubed divided by pi cubed. So that's the density of points in my k-space. Now, in what we call the continuum limit, that is, this L gets very, very large, you see the spacing between points in k-space gets smaller and smaller and smaller. It goes like pi over L, right? Or in other words, the density of points in k-space, this density here, gets very, very large. Gets very, very. So it's getting, as I make the system larger, I go to this continuum limit. My points in k-space are getting it's closer and closer together. So it's in this limit we want to know the number of modes labeled by this wave vector. We want to know the number of modes having magnitude in the interval k to k plus dk. And we'll denote that that is a density of states in k-space, or in wave vector space. And the number of modes in this interval we'll call it f of k dk. So f of k is the number of modes per unit wave vector. And of course, if you think about something that has a given magnitude, basically it'll be the number of modes. We'll have this plot again, except we could label these by k values. It's the number of modes. We want to find the number of modes in a thin shell, right? So if all the modes between k and k plus dk are the modes in a thin shell at radius k here. Let's say it again. So we'll consider L to be large, and so we'll take the number of modes in a spherical shell at radius k, and we'll find the number of modes in that shell. And it's going to be 1/8 because we're only taking the positive quadrant. So there are, in 3D space, there are 8 quadrants, and every place where the k's are positive is 1/8 of a sphere. And then this factor here is the volume of a spherical shell at radius k. So it's the surface area, 4 pi k squared, times the thickness, dk. So that's the volume of our spherical shell. And of course, as we had before, this is the volume of a point in k-space. So if each point occupies pi L to the cubed, then if this is the volume of our spherical shell, and that's the volume of each point, then this is going to be the number of points in this shell. So that's how it works. It's actually quite simple. Now, there's another way to get this, which is also relatively simple. We could consider the total number of wave vector values with magnitude less than k. That is, that's everything contained in a sphere of this positive quadrant. So we could consider that instead. So that's just 1/8 again times the volume of the sphere, 4/3 pi k cubed dk. So that's the volume, and then we divide again by the volume of a single point in k space, and that gives us the total number of points in that quadrant. And it has this formula. And of course volume is L cubed here. And then we could take the derivative to get the number, to get the points. So this is actually a mistake here. This dk needs to be removed. Yeah, because this is total number of points. We take the derivative of this guy, and we find that this f of k is of course the derivative with respect to k of this big gamma k. Without that, that's a mistake. I'll get rid of that. And you see we'll get the same thing actually. So here you see we have basically 2 and pi squared. These are the same, you can see. So that's it. We've sort of found the number of modes per unit wave vector in k space. It's just k squared over 2 pi squared times the volume. So of course it grows like the volume of our box, because as the volume gets larger, the points are getting closer together, of course. And that's the answer for the density of states in wave vector space. It's just k squared over 2 pi squared times the volume. But like I said, we want to calculate the partition function, so we need to know how the energy depends upon this wave vector k. And of course, that depends. So that's if we wanted the density of states and energy, which is what we're going to do. Now, we could move from here and find the DOS and frequency, and then we need to know the angular frequency as a function of wave vector. So this is more important, for example, in phonons and photons, and we'll see that later in the course. But here we have the density of states in wave vector, and we'll just need to know how the energy depends upon this k to get the density of states in energy. And so that's easy. So let's consider free particles in a box, which as opposed to photons, we'll consider actually non-relativistic free particles. And we know the relation for this. For non-relativistic free particles, the energy is the momentum squared divided by 2m, p squared over 2m. And p squared, of course, is h bar k, where k is the wave vector. So here we have the relation epsilon equals h bar squared, k squared over 2m. And so this allows us to start. So now we can move from the density of states, or the number of modes with wave vector between k and k plus dk, which is our density of states in wave vector. And we can just change variables to find this, what we want, g of epsilon. So the number of modes, so we start with this equation. It just says the number of modes in energy between epsilon and epsilon plus d epsilon has to be the number of modes in wave vector that are in the interval k to k plus dk. So that's just conservation of number of modes, really. And so you'll see then that their g of epsilon is basically f of k times dk over d epsilon, or we could write it as f of k divided by d epsilon by dk. And since we have this, we can find d epsilon by dk, right? And so that's all we have to do. It's a change of variables. It's much like we discussed earlier in the course. And so to do that, we just, we write, here's k squared over, here's our density of states. Let's see, k squared over 2 pi squared volume. That's our density of states in k space. And then this is the derivative. And then, of course, we just have to, we want to get this in terms of epsilon, so we just have to substitute we just solve K in terms of epsilon and plug that back in, and lo and behold, we get this formula when we sort of arrange terms in a more convenient way. And so the main thing to notice here is that the density of states in energy goes like the square root of energy, right? So it goes epsilon to the power 1/2, and it has this constant out front. So this is just a constant, but it's still proportional to the volume. So that's it. That's our density of states in 3D for particles in a box. Now you'll see you get a different dependence in 2D and 1D of these density of states, as you might expect. But that's what we'll work with now. So now we have that, we can move on and solve some more interesting problems. Okay, and so the first system we're going to treat with this approach will be the ideal Fermi gas. Now there are several examples of nearly ideal Fermi gases. The one we'll use mostly, we'll use in this lecture, will be a Fermi gas that we find in metals, let's say. Next week we'll discuss Fermi gases in neutron stars, and there are other examples. But for this lecture we'll discuss a very standard kind of example, and one that's very useful, basically electrons in a metal. So basically we have a metal, we have atoms in a metal, and the electrons in the valence states, the really weakly bound electrons in our metal, become delocalized, and they essentially behave like free particles. So we can treat them as if they're free particles. Now, so we'll treat them using the so-called free electron model, which we'll assume to be an ideal Fermi-Dirac gas. Well, of course, the electrons in a metal interact with the positive ions and other electrons, and we're going to neglect this. But it turns out this is very successful in explaining many features of metals. In fact, it's kind of astonishingly good, and I mean later on you'll see that even when you have interactions between electrons, you get essentially, effectively, a kind of free electron behavior in a metal. Now, that's beyond this course, but this is this simple idealized system turns out to be very, very successful, and we'll discuss why that is a little bit after we derive some of the properties. So we're going to assume non-interacting fermions for our electrons, and then of course the mean number of fermions we'll call capital N. We'll understand that in the large N limit the fluctuations are really small, so we'll just write N. Total number of electrons is just the sum over the energy states labeled by R of the mean occupation number for that state, this expectation of N sub R. And of course we've seen this before, it's just the sum over R of these factors for each state. So if we consider free fermions, our electrons are free fermions confined to a box of volume V, and we consider the volume getting very, very large, basically we'll be able to convert this sum to an integral. So the volume's getting large, the energy levels, the density of states we worked out, let's go back here, you can see it's getting very, very dense as the volume increases. Instead of using the sum, we'll convert it to an integral, and we'll integrate this over the density of states that we just derived, this g of epsilon. Now, for this model of electrons as an ideal Fermi gas, we'll also need to include a spin degeneracy, s equals 2, and well, spin 1/2 electrons. So basically, we can just stick that in this g here. This is what we found when we derived density states, and we'll just put this extra factor of 2 here, like we discussed in the very beginning of this lecture. So then the the density of states becomes this here, what we found before, just multiplied by 2. Okay, so now we're ready to go. So, well, that's our density of states. We can also find the number of fermions, or the mean number of fermions with energy between epsilon and epsilon plus d epsilon is given by, we'll call that d capital N sub epsilon. Well, that's just equal to this mean occupation number, N bar. So I'm just going to, for simplicity, I'm going to write these as N bar, and I'm going to explicitly show it, it depends upon epsilon and mu. And of course, it's just this factor, which is the Fermi-Dirac distribution. So the mean number of fermions here will be this factor which describes the occupancy times the density of states, this factor, right? So we'll just combine those two together and it looks like this. And so when we move to an integral, then include this sort of effective degeneracy, which is given by the density of states and the spin, that becomes an integral. We'll see this, we have to integrate instead of sum over the energy, this guy, this term. And so what does that look like? Well, in the general sense, for arbitrary chemical potential and temperature, it's just the integral as the energy goes from 0 to infinity of the density of states times the mean occupancy, or the Fermi-Dirac distribution here. And so it looks like this. And if we write it all out, then here's what we get. And I've pulled out the constants out front, and what we have to integrate over then is this epsilon to the 1/2 square root of epsilon, basically. Square root of epsilon, which is from our density of states dependence, and this factor here, which is from the Fermi-Dirac distribution. Now, this integral for arbitrary beta and mu is not so simple, and there are, there are ways to calculate this numerically, or there are some approximations that we'll probably cover later. But we're going to see now that basically this constraint determines the chemical potential for a number of electrons once we have the volume and temperature fixed. And so we have discussed that before. So basically, if we want to fix in, we have to adjust the chemical potential. So when we integrate over these states, we get that value. Okay. That is, if we fix volume and number, we'll find the chemical potential as a function of temperature. So once again, let's just look at this thing in the brackets here, which we call dN by d epsilon, which is the product of these two terms. This looks like what we saw before because of this mean occupation number, this Fermi-Dirac distribution, we multiply that times this density of states. So at 0 temperature, this is our square root. The blue curve is our square root dependence of our density of states, and then of course it gets chopped off here at 0 temperature when at the Fermi energy by this factor here. And as we turn up the temperature, it gets smoothed out a bit. And so what we have to do is we integrate this to find the number of particles. So, and in general, that's we have to evaluate this integral, but we can do this quite easily at 0 temperature because of course the Fermi-Dirac distribution is a step function, and it goes from 1 to 0 at mu equal to this Fermi energy. This should be Fermi energy. We'll see how so the Fermi-Dirac distribution in terms of mu and epsilon, of course, goes to 0 when mu equals epsilon. And we'll see how that works. Since we can only put one particle per state, because we're going to handle the spin degeneracy outside of this, We imagine we have these single particle states, epsilon. We start at epsilon 0, we go to epsilon 1, epsilon 2, and the way we've chosen it, we have the 0 at the ground state. The very lowest energy state is epsilon 0 will take to be 0. But they're ordered this way, so we start filling these states. Then you can see that at t equals 0, we have n particles. We filled the n lowest energy states. So in order for this Fermi Dirac distribution to describe our system, then we know that at 0 temperature, mu has to be the Fermi energy. And I probably should use little epsilon here because I used that in the rest of the lecture, but that's the Fermi energy. So basically, the chemical potential is the Fermi energy, which is the topmost occupied level at t equals 0. And that means that, for energies below the Fermi energy, this Fermi Dirac distribution will equal 1, and it will drop rapidly to 0 at the Fermi energy, which is just saying that we've filled the n lowest energy level states. And so it's very simple to get the chemical potential at 0 temperature. It's just the topmost occupied energy. That's the Fermi energy. Yeah, apologies. I should have used epsilon here, like I did here. And usually I'll refer in this course to the Fermi energy as little epsilon sub f. So then, so it's very easy to find the Fermi energy for our, fermions in a box. Since at t equals 0, we just have to integrate 0 to the Fermi energy, right? So this, if we go back to this integral here, this is 1 up to the Fermi energy, and then it's 0. So it means we can just integrate the density of states up to the Fermi energy, and then stop there and this is just a 1 up there. So in the end, we get a very simple integral. We just integrate. We can, at t equals 0, the number of particles is just integral from 0 to the Fermi energy of the density of states with d epsilon. And we plug in the formula we found, and we get this. And of course, we can integrate that. And lo and behold, we get the number of particles in terms of the Fermi energy, which we can turn around and we can say, or we solve for the Fermi energy. The Fermi energy is this value, right? It comes from this constraint, basically. And that kind of makes sense if I have particles in a box and I have more there. Of course, the Fermi energy is going to be larger and larger, depending upon it's actually the number of particles per volume. So it's actually the density here that comes into affect the number density to the 2/3 power. Yeah, so we see the Fermi energy depends on the mass, of course, and the concentration, or so-called number density. Okay, so now we have the Fermi energy. Okay, so if you actually do this and you put in the electron mass, and actually in solids, what happens is you get an effective mass. You'll see that when you take solid state physics. But if you plug in the sort of effective mass for a metal, for most metals, and the number density, which is really just given by the density of the material, you'll find that the Fermi energy is an order of a few electron volts in it. This is an energy unit we typically use in atomic and solid state physics. And a few electron volts corresponds to a Fermi temperature. So we can say we have the Fermi energy. Apologies again, I should use consistent notation. I should have epsilon sub f here. Well, you can think of that as a temperature if you define the temperature so that Kb times Tf is the Fermi energy. And you'll find for the Fermi energy in metals, a few eV corresponds to tens of thousands of Kelvin, right? By the way, a very nice relationship that is very useful is that the temperature of 1 Kelvin, kBT, corresponds to 86.2 micro electron volts, 10 to the minus 6 electron volts. This is a very useful relation. This is a very useful way to remember Boltzmann's constant, essentially, in these units. So if you plug that in, you'll see that a few electron volts is tens of thousands of kelvins. So the Fermi temperature is quite high because usually the temperature, even when we're here at room temperature, which is 300 Kelvin, the temperature typically is much less than this Fermi temperature, and we'll see that has very interesting consequences. It essentially means that we can use the zero temperature results a lot. We'll come back to that. That's what it means for metal. And we'll see this in several examples. I mean, because of the nature of fermions, that they can only occupy, you can't put arbitrary numbers of them in each state, then usually the Fermi energy turns out to be quite high, higher than the temperature that you're usually interested in. So a lot of times the results that we derive for zero temperature are actually quite useful, surprisingly useful. We'll see that more in the course. Okay, so we've found the Fermi energy for our particles in a box, our fermions in a box, and its dependence on the mass and the concentration. Okay. And we'll come back to some more calculations, but I just want to go back and look at this density in K space. So this is a little aside. So we'll come back to the Fermi gas in a minute. I just wanted to mention something that you'll see if you read other books and things, and it is in the textbook. I think it's not handled very well in the textbook, so I'm just going to mention it here. So if you remember back at the beginning of this lecture, we derived the density of states, and the way we did that is we started with the density of states in K space for our particles in a box. And we started with this wave equation, and we assumed solution of this standing waves to match the boundary conditions of this product of sign functions, and that allowed us to get the allowed K values, right? Well, another possibility you could do is you could assume solutions that are exponential forms, so e to the I kx times x, y, and z, and you'll find that these solutions also have, in the satisfy the boundary conditions, the wave vector will have to be the only allowed wave vectors will be of this form, where nx and ny and nz can take on positive and negative values, but instead of before we had pi over L, now we'll have 2 pi over L for the allowed values of an equation of this form. But you'll see that also that you have to take a superposition of these solutions, these exponential solutions. That's how you get sines and cosines, as you know. So you'll need, if you select a k, you'll need to also minus k. You'll need to combine those two to match to actually satisfy the boundary conditions, but also to be a time-independent quantum mechanical eigenstate, which can always be taken to be real. So we could do this approach, and the advantage of that is that I have k. I need to take both k values, but I have k not just positive. I have k positive and negative, right? And so in this approach, the spacing between the nearest points on this axis is 2 pi over L instead of pi over L. And you can think of now the K-space volume occupied by one point is 2 pi quantity cubed divided by L cubed, and a density L cubed over 2 pi cubed. And you see this density is in 3D is 1/8 what we had previously. But that's okay, because now we can integrate over the whole sphere in wave vector space instead of one quadrant, so which was 1/8. So the result is, you get the same density of states in K space, since now we're taking the whole spherical shell in K space instead of 1/8, and so now the 1/8 basically gets shoved in this factor instead of out front because we're only considering 1/8. So in the end you get the same answer, and so why bother? Well, this is just the way it's approached in other places. And then, I mean, it's kind of, and so that means you get exactly the same density of states and energy. So the only thing is it just allows you to picture some things a little bit differently. So if we think about t equals 0 and this density of states, it gets chopped off. That is, we fill our fermions up to some level, the Fermi energy, and so everything below it's filled. Then, and because we have this relation between energy and wave vector, we can see that the filled states correspond to a sphere. Our field in energy we have this cutoff, but in momentum it means in this wave vector space we have sort of we fill all the states up to in wave vector, in the sphere and wave vector space, up to some radius we call the Fermi wave vector, and of course it has this value. We've just solved this for k and plugged in the Fermi energy, and we can write that down. And this gives us the surface of this sphere is called the Fermi surface, right? And so you'll hear that term. And so here's a kind of a picture of the Fermi surface. Everything here is filled, and the surface of this sphere is the Fermi surface. And so it has this nice picture that as the temperature is raised, some of the fermions inside are excited across the surface outside, which is actually higher energies. So it's just a slightly different approach and gives you a picture of a whole sphere in k-space. And this is usually what is used in, for example, solid state physics, as you'll see if you take condensed matter solid state next year or next term, or term, I guess it's term 2. Yeah. Anyway, just a small digression now. Now we'll get back to calculating some things. So we found the Fermi energy. So let's do one last thing for this lecture, because I think we've introduced enough new things. But now that we found the Fermi energy, let's do something. Let's calculate the mean energy of our Fermi gas at 0 temperature. And to do that, of course, we just have to integrate. So we'll just have to do what we were doing previously with sums. We'll just do this with integrals now because we're in this continuum limit. So the mean energy, of course, is 2 because we're considered spin 1/2, and we have the spin degeneracy. And then we're going to integrate. So we're going to integrate from 0 to infinity times the density of states, the mean occupation number, or the Fermi-Dirac distribution, and that gets multiplied by energy, because the number of particles, of course, so the energy is just the energy multiplied by the mean occupancy, and then, of course, the effective degeneracy, or this density of states, in an integral. So we have this integral, and of course at t equals 0, it's really easy because this factor is 1 up to the Fermi energy and 0 above that, so that chops off our integral and means we just integrate epsilon times the density of states here from 0 to the Fermi energy. And so we can do that. And if you look in the textbook, he does this. And you could do that. We could just plug, if we wanted to, we could do this directly. We could plug this into that integral, and we have all these constants, and we have this epsilon to the 1/2. And this epsilon to the 1/2 gets multiplied by that epsilon, so it becomes epsilon to the 3/2. But we have all these constants outside. We could do that, and what we'd like to see eventually is we'd like to see how the mean energy, the total mean energy, so the mean energy of the total system, we'd like to see how it's related to the Fermi energy. And so we could do that, and we'd have all these constants, and we found the Fermi energy way back here, right? And we could do a lot of algebra, and it's actually a lot of work, and whenever I do this I make a lot of mistakes. Sorry, we're back here. So we could do that, but I'll show you a really nice trick that you can use for these calculations. Actually, it's a couple of tricks. It's a nice trick, but it has 2 parts. So if you want, convince yourself and go look at the textbook and put that there and do the integral and get it in terms of the Fermi energy by substituting what you found in the Fermi energy. It's a bit of algebra, but here's a nice little trick. So since we already found the Fermi energy here, and basically it has it depends upon, of course, 1 over the mass and the concentration, That's what we found before. Since we know this, you see this density of states involves the volume and the mass and H to keep all these things. Let's rewrite. It would be very helpful if we we're able to get the density of states here in terms of the Fermi energy, right? And you could do that. You could say, oh, okay, well, let me solve this for volume, and I'll plug in the volume there. And that's also a lot of algebra to do, and opportunity, and taking powers and stuff. It's kind of a pain. So here's another trick. We could do this by direct substitution, but here's the trick that goes with this trick. Let's just write g of epsilon. We know it goes like epsilon to the power 1/2. So just write it a times epsilon 1/2, and a is a constant we'll find. So, and we do this and we'll find this from t equals 0, right? This was our constraint on total numbers. So just plug in a epsilon 1/2, and we know we have to integrate to the Fermi energy. And so that's a times this integral, which is really simple to do. And we get this value, and now we solve it for a, and we get a equals 3 large N epsilon Fermi energy times to the power minus 3/2 divided by 2. And so that's it. Now we have G in the right form now. We have it in terms of the Fermi energy, which looks a lot neater, and we still have this dependence. And so now it's very easy to find the mean total energy because we substitute that in, which is a lot nicer, and we just have this simple integral, and we can do that, and lo and behold, we find that the total mean energy is basically 3/5 times N times the Fermi energy. Quite simple result. So that's a nice little trick, and using this form of density of states usually is very, very helpful in lots of calculations. We'll see it again, and you can go back and look and see how I did it. Okay. And so this, well, we think about this. Does this make sense? Well, yeah, it makes sense because the mean energy per particle is basically, oh, I made a mistake here. Mean energy particles, I divide by N. Sorry, that should be a 5. I'm just dividing this. So the mean energy particle is 3/5 the Fermi energy. Let me correct this on the notes before I upload them, which of course makes sense from this plot, right? Here's so basically this is, yeah, I have it correct here, 3/5 epsilon Fermi, right? Which lies right there. And of course, if I found the mean of this over this distribution, that's what I get. It'd have to be, since it's larger here than here, it would have to be larger than half. So that answer does make sense. Okay. So that's enough for this lecture. We'll pick back up with the ideal Fermi gas in the next lecture, and we'll calculate a few more things, and we'll look at another important result, which is called Pauli paramagnetism. And there's a lot we can actually calculate now with the properties of an ideal Fermi gas now that we've done this. So go back. So the important things in this lecture were that we learned to go to continuum limit, and to do that we had to derive a density of states. So the density of states is a really important concept, and so you should know how that comes about. And we'll use that again and again. And then there was this finding the density of states for a Fermi gas in this really helpful form as well. Okay, so that's it for today's lecture. I will see you next time, with our next lecture, I guess, later in this week, tomorrow. And until then, take care and see you next time.